BXB. It's in the game!
Hi there, and welcome back to another episode of Let's Learn About Video Games, an occasional video series that tries to demystify the technical side of how video games work under the bonnet. My name is Adam Breeden, and this time I want to talk to you about optimization. And as with my first video on frame rates, my reasons for wanting to do so are mostly to correct some of the common misconceptions around the subject. In fact, optimization is a pretty strong contender for the title of game dev term most misunderstood by gamers. And I don't really blame gamers for that. The games industry itself has to carry a good chunk of the blame here. For years now, developers have talked about optimization as if it was some kind of magical process that will transform a tepid, middle-of-the-road experience into the next gaming mega hit. Now unfortunately, the reality of optimization isn't quite what this hyperbole would lead you to believe. So, before we get into the technical details of what it actually means, let's start out by addressing two of the most frequent misconceptions I see online. First up, the idea that optimization is an inherently positive thing. Now that might sound odd, because who wouldn't want to play an optimized game? I mean, by definition, it's optimal, right? Doesn't optimal basically mean perfect? Why wouldn't you want that? Well, the thing is, optimize is a pretty Orwellian word at times. Imagine your employer calls a big meeting for the entire company one day, and they start this meeting off by explaining that they've gathered you all here to tell you about their new plans to optimize the workforce. How would you feel about that? Suddenly you start to see that optimal doesn't always sound quite so desirable. This other, rather more reductive meaning of the word optimal is often what optimization really means for video games. It's always worth bearing in mind that by far the most common optimization technique employed in game development is the trusty delete key. And whilst I'm not saying that's necessarily a bad thing, I mean, removing costly elements from part of the game in order to keep it running smoothly is a perfectly reasonable thing to do. It's a far cry from the magical improvement that many people still envisage when they hear the term used. And while I'm talking about magical improvements, the other big myth that I'd love to see the back of is the idea of the mystical code wizard. I'm sure this is what the average gamer thinks is happening when they hear that a game is being optimized. The mental image that most people have is of some gnarled old genius who comes in and dives deep into the game code, meticulously stripping out inefficiencies, using their decades of experience and their technical wizardry to prune away unneeded actions from each function until the core code of the game is executing twice as fast as it was before. Now the problem here is I can't say that never happens, but I can tell you that in 15 years of experience as a game developer, I've maybe seen it happen 3 times in my life. The simple reality is, computers nowadays are so staggeringly fast. That kind of hand optimization just isn't worth the effort anymore. Consider these numbers. The CPU of the Xbox 360, not the Xbox One, the 360, can perform several million mathematical calculations in a single millisecond. So now you have to ask yourself, how many operations does our code wizard need to optimize away in order to boost performance by even a single frame per second? Now, I won't bore you with the maths I did to calculate this, but by my reckoning, I think they need to find somewhere in the region of 2.5 million in order to get this benefit. As I said, that's not impossible. Small inefficiencies in very frequently called sections of code can quickly mount up, but I think you're starting to get a sense of how unlikely that outcome really is. So okay then, if those things aren't optimization, what is? Well, to answer that, you're going to need to know a bit more about what actually limits game performance, and so, once again, it's time to get technical. When a computer builds a frame, the work involved is split across 2 different elements of the hardware. These 2 elements have, unfortunately, very similar names, and I'm now going to have to say them about 1,000 times each. Honestly, the rest of this script is such a tongue twister, I'm surprised a fox in socks doesn't show up halfway through it. Anyway, these 2 elements are the CPU, which basically figures out what's happening in the game, and the GPU, which is what actually draws the frame, renders the image, and handles sending it to the monitor. Now, for the purposes of the following explanation, I'm going to talk about these two elements as if they operate simultaneously when it comes to building a frame. But in reality, this isn't strictly true. The GPU can't really start building the frame until the CPU has already told it a bunch of stuff about the current game state. In the interest of keeping my diagrams and explanations as clear as possible, I'm going to basically ignore this fact. But if that inaccuracy bothers you, you can assume from this point onwards that every time I talk about the task list the GPU is performing, the first element of that list is a long task called wait for the CPU to tell me what the hell is going on. I'm pretty confident that with that in place, all of my examples do still reflect reality. I mean, I hope so. Games are really complicated. But now that that's out of the way, let's get back to talking about those two elements. Here's one example of what might be happening when you build a frame. As you can see, the CPU here is finishing everything it needs to do in 10 milliseconds, whilst the GPU needs 14 milliseconds to get all of its work done to build this single frame. The end result of this is, obviously, that the frame is taking 14 milliseconds to build, and the CPU is sitting idle for the last 4 milliseconds of that process because it doesn't have anything to do. It's cleared its tasks. The GPU here is obviously the bottleneck for our game, or, as a developer would put it, this game is GPU bound. But now consider a different game, one in which the roles of these two elements have been reversed. Here the CPU is taking 14 milliseconds to do its stuff, whilst the GPU is getting its workload shifted in 10 milliseconds. This time it's the GPU that is idling at the end of the frame building process, and the CPU that is the bottleneck to our speed. It won't surprise you to learn that a developer would call this game CPU bound. Okay, so we've got our lingo sorted. Now let's see what we can do to get these two games running faster. We'll start by looking at game number 1 again, the GPU bound game. Given that we have a CPU that does nothing for 4 milliseconds every frame, it's hopefully fairly obvious that what we ideally want to do here is transfer some of the GPU's work over to the CPU. If we could get the CPU to just step in and help out for a couple of milliseconds, we'd be down to only needing 12 milliseconds to build the frame. Now unfortunately, you can't do that directly. The two pieces of hardware involved are just too different and they can't do each other's jobs in that way. But maybe there's a way to achieve this end indirectly. Perhaps we could just make the GPU's job a bit easier, and if that costs us making the CPU's job a little more difficult, so be it. Check out this spaceship. If this spaceship is on screen, the GPU has to draw it. That's obvious, right? Otherwise, no one would get to admire my fabulous artwork. But because this spaceship is all one object, the entire spaceship gets passed to the GPU as a single rendering task. This means that the GPU has to draw all of it, even if just part of it is on screen. But what if we split that spaceship up into chunks like so? Well, now that spaceship is in 3 separate bits, and if one of those bits is off screen, the GPU won't be given that bit to draw. This would reduce the amount of work the GPU has to do. The downside to this is that the CPU now has to treat that spaceship as if it were 3 separate objects. It's doing 3 separate visibility checks, it's doing 3 separate movement updates, and so on and so forth. So the CPU does now have to do a little bit more work. But that's exactly what we said we wanted, right? The GPU's job has gotten slightly easier, and the CPU's job has gotten a little more complicated. But since we were GPU bound, the overall effect is that our game is now running faster. Now let's look at game number 2, the CPU bound game. Can we make a similar trade in the opposite direction? Well, yes we can, but we have to use a different technique. Check out now this squadron of spaceships. These spaceships are very different from the one in the last game, obviously. Right now the CPU is having to treat these as 3 separate objects, and that means 3 different positions to deal with, 3 different visibility checks, 3 different movement updates. It's doing 3 lots of work. If splitting one object into 3 helped move the workload in one direction, maybe doing that process in reverse will move the workload in the other direction. So let's merge these ships together so that they become a single, larger object, like so. Well, now the CPU can treat them all as a single object. It only has to track one position for them. It only has to do one visibility check for them. Now, of course, if we do need to draw them, they are all now just one big task for the GPU, and so the GPU ends up drawing all three of them, even if some of them are off screen. That means that in this case, we've lightened the workload of the CPU at the expense of making the GPU work a bit harder, which again is exactly what we wanted. So there you go. That's just two of many techniques that developers can use to redistribute the workload across the computer's hardware. Hopefully, if you understand those two, you now have a good baseline understanding that you can use yourself to figure out some of the others. Whatever the technique employed, the basic principle is always the same. You take the strain away from the bottleneck by passing it over to the other element. This idea is what underpins nearly all optimization in modern games. I mean, apart from the deleting stuff. Never forget the deleting stuff is always the number one tool. I think that about covers it. Once again, I want to thank you for sticking with this video to the end, and I hope you got something useful out of it. If you are enjoying this series and have anything specific you'd like to see me cover, feel free to leave a comment or get in touch with me on Twitter. I'm very keen to make sure that this series is addressing the issues and topics that gamers are genuinely interested in, and so a bit of guidance here would be a great thing. In the meantime, all the usual YouTube stuff applies. I mean, likes and subscribes are always appreciated, and they do have a serious impact on how often this video shows up in people's searches. And until the next time, thank you for watching. I've been Adam Breeden, and that was another brief insight into how games work.